Hello everyone, this is Mayur here from SARODEOVERWIRELESS Consulting. Today I would like to present a short analysis on antennas and path loss. Let us begin to understand the Freeze formula. The Freeze equation is a very well-known formula which relates the incident power to the transmitted power from the antenna and to the gain of the transmitter and the receiver, and a component called the path loss, which is directly proportional to the wavelength and inversely proportional to the distance between the antenna square. On the top right, you can see the path loss between 2.4 and 5 GHz band. You can observe that as distance increases, there is a fixed 6 dB delta in path loss between the 2.4 and 5 GHz band. So does this mean that the RF wave propagating in the 5 GHz band is dissipating energy? Let's look into a graph on the top, on the bottom right. It's basically an attenuation with frequency due to absorption from H2O and O2 in the atmosphere. You can see that the oxygen absorption is the same between 2.4 and 5 GHz band, that is shown by the green curve, and the water absorption is it only increases by 10 to the power minus 3 dB per kilometer. That's really small, and it is up like for per meter it is 10 to the power minus 6. So we can conclude from this graph that there's no losses because of absorption between the 2.4 and 5 GHz band. So let's try to explain what causes the 6 dB delta difference between the path loss between the 2.4 and 5 GHz band. So the 6 dB path loss is due to the antenna aperture size. Let us try to understand what is antenna aperture. So antenna aperture is an equivalent area over which an antenna extracts energy from the passive radio waves. So to understand this, let's imagine that an isotropic antenna is placed at origin of an X, Y, and Z coordinate plane. Now we are trying to understand the amount of power that was received by a sense antenna, which is also isotropic in this area defined by A, which is given by PT, that is the transmitted power from the isotropic antenna, times the area of this square divided by 4 pi d square, which is the surface area of the sphere. For an imaginary isotropic antenna, the transmitted gain and the received gain is equal to 1, and the effective isotropic antenna aperture is given by lambda squared by 4 pi. Now this can be derived. I would not like to go into derivation in this presentation. You can take a look at a reference which I have quoted, and using the laws of thermodynamics you can actually derive this, and this is the crux for understanding the impact of antenna aperture on path loss. Now substituting the antenna aperture for isotropic antennas into the formula above, we come to this equation where received power is transmitted power by lambda by 4 pi d square. This equation looks familiar. We just don't see familiar to the Freeze equation, but we don't see the gain parameters. So imaginary isotropic antennas do not exist in real world. In real world, the most omnidirectional antenna you can find is a dipole antenna. For a half wavelength dipole antenna, the gain GT and GR is given by 1.64, and then the effective antenna aperture of a dipole antenna is gain times lambda squared by 4 pi. Substituting this antenna aperture in the equation above, we come to the formula. Received power is 2.69 times transmitted power by lambda by 4 pi d whole square. This equation looks familiar, right? the Friese equation is given here. So what we have derived here is that the antenna aperture is smaller at higher frequencies. That is due to the shorter wavelengths. And the 5 gigahertz antennas capture less RF energy as compared to 2.4 gigahertz, and that contributes to the 6 dB path loss. So let us now try to understand the real world implications of path loss. Any Wi-Fi user would tell you that they experience a better coverage in 2.4 gigahertz band as compared to 5 and 6 gigahertz band. We have discussed the impact of the antenna aperture on the path loss that is valid for free space, but we are never using Wi-Fi or any wireless technology in free space. The Friese equation is valid for free space communication, and it takes an assumption that the transmitter and receiver in direct line of sight. In a home environment, you seldom have a direct line of sight between your AP and the stay. Wi-Fi signal has to pass through concrete floors, brick walls, wooden and plaster walls, all of which attenuate the RF signal, and that attenuation increases with frequency. Also, the Wi-Fi signals in residential or enterprise environment, anywhere indoors, will undergo attenuation due to Rayleigh fading, and that is caused by reflections, scattering and diffraction of Wi-Fi signals, which also increases with frequency. So along with the antenna aperture size, the losses of RF energy because of attenuation by materials present in a home, in a residential environment, and the fading would cause degradation in path loss. The graph below, you can see an example of a fading in a typical home environment, where the x-axis is time and the y-axis is the signal strength, and you can see over time the signal varies between -40 to -20 dBm. So there are some very deep fades. Thus that contributes to a degradation in received power. So along with the small aperture size, channel properties and environment play a significant role, a significant contribution to the path loss. And how can we model this? Can we model these channel impairments? That is something we will discuss in our next presentation. I would like to thank Keith Parsons for bringing up this concept of antenna aperture in one of his presentations on 6 gigahertz Wi-Fi. As mentioned by him, there is a common misconception that path loss increases with frequency. That's because of how the wave propagates through air, which is not completely correct. As we have discussed, the increase in path loss is due to the antenna aperture and also due to the absorption of the RF wave through different materials and the properties of the channel, specifically fading. There are also other great references which you can take a look. Thank you for your time. I really appreciate any comments, and I hope to bring you more insights in my upcoming presentation. Thank you and have a great day.